It is a pleasure to introduce our speaker, Azhar Ahmed, from the North Dakota State University. The title of his talk is Discrete Subgroups of Diffeomorphism, Groups of Compact One-Manifolds.
Thank you very much. It's a pleasure to be here and to listen to so many interesting talks. Let's see how mine goes. So this is a talk about discrete subgroups of diffeomorphism groups of compact one manifolds. So I will even consider some manifolds with or without boundaries. In any case, we don't have too many of them to talk about. So really maybe circle and interval. So if we essentially consider connected ones. For many questions that I am considering, the interval case is actually harder than the circle case. So I will concentrate on the interval, actually. So when I say compact one manifold, we can just concentrate on interval 0, 1, essentially. Also, I will be talking about discrete subgroups, but my aim is also to go in the direction of lattices of these huge diffeomorphism groups and try to define them. As I have done in one of my papers. So I will start with just reminding very quickly some facts about Lie groups, just to put things into context, and then talk about discrete subgroups and then lattices of diffeomorphism groups, and then discuss one bright application actually of my study of discrete subgroups. Which is an old problem which I was able to solve, but actually using my study of discrete subgroups. So I don't know any other way of really going about that problem. So Lie groups, they are isometry groups of some important geometries. That is maybe aligning more with Klein's approach to Lie groups. And more traditional definition would be a manifold. It's a manifold and a topological group where these two structures are respecting each other. Of course, some important examples, we see orientation preserving isometries of Euclidean space and orientation preserving isometries of hyperbolic plane. So just examples of Lie groups. We always can concentrate on connected components of Lie groups. So we'll assume that our Lie groups are connected. Then we have maximal compact subgroup always, which is unique up to conjugacy. And topologically, the Lie group splits. So we have this, this notation denotes topological, it denotes diffeomorphism. So we have compact subgroup, maximal compact subgroup times Rm, where M is just the dimension of differences. For example, for SL2R, we have topologically just S1 cross R2. For SL3R, it will be actually a bit more complicated. So the compact factor turns out to be diffeomorphic to RP3. So we got some interesting maybe topology there. So the examples we are looking at are simple Lie groups, SL2R, SL3R. For solvable Lie groups, their maximal compact subgroups are just tori, turns out, topological. We see in the case of SL3R, already we have something like RP3, which is SO3. Yeah, so now I'm defining a discrete, so a lattice. So a lattice of a Lie group is a discrete subgroup of finite covolume. So here the volume, the covolume is understood in the sense of Haar measure. So as any local compact topological group, a Lie group admits a left invariant Haar measure, which is unique up to multiplication by a positive constant, and a unique right invariant Haar measure. They may not coincide. If they do, we call the Lie group unimodular. For example, a co-compact discrete subgroup is always a lattice. So Zn is a lattice of Rn. When we talk about co-volume here, we are really computing the volume of the Lebesgue measure of a cube, which is finite. And in fact, any lattice of Rn is isomorphic to Zn. But look at the next example. SL2Z is a lattice of SL2R, but it's not co-compact in SL2R. And speaking of SL2R, so we have co-compact and non-co-compact lattices, and co-compact lattices are virtually surface groups, so hyperbolic surface groups, pi1 of some sigma g, when g is at least 2. And non-co-compact lattices are, as a group, they are just virtually free groups. For example, SL2Z is a virtually free group. Okay. Of course, when we go beyond SL2R, we have a very rich variety of lattices. So it's hard to really describe in these simple terms, like give some very simple characterization or classification. Look at this group now. It's a two-dimensional Lie group. You see we have in dimension 2, let's see, we are talking about over rails, everything's over rails. So, we have only 2 Lie algebras in dimension 2. One is a commutative Lie algebra. The other one is actually the algebra of this group that we are seeing. It's affine homeomorphisms of real line, orientation preserving homeomorphism. So A is positive. So these are just maps AX plus B. A group as simple as this is already very interesting. For example, it does not admit a lattice, actually. So it's a two-dimensional solvable Lie group. Topologically, it's just R2, upper half plane, which is just R2. It does not admit a lattice. And it's easy to see that because if a subgroup is not cyclic, then it's not discrete, it turns out. It's easy but interesting exercise. And any cyclic subgroup can actually compute the co-volume directly if you want. Or you may say, you're using either left invariant Hard measure or right invariant Hard measure, and you see this group is not unimodular already. So left and right Hard measures are different. Look at the left invariant Hard measure, for example. You will see it is the same formula as the formula for the hyperbolic area in upper half plane. You can use either one for any discrete subgroup, and for any discrete, for any cyclic subgroup, you can easily describe the fundamental domain, and then using any of these measures, you will see the fundamental domain has infinite measure. So this group affine homeomorphisms of R does not admit a lattice, a remarkable fact already in dimension 2. Now, for a Lie group, we have Levi decomposition. It's at the level of Lie algebra, is also at the level of groups too. Now we have solvable part and then semi-simple part. A lattice does not quite split, so there's some complications there. But more or less, we can reduce ourselves to studying lattices of solvable Lie groups and then lattices of semi-simple Lie groups. These are two kind of opposite worlds, very different worlds. The study of lattices for solvable Lie groups has been extensively studied. I think started in the 1950s, if I'm not mistaken, mainly by Masta, and he shows that any lattice there is actually co-compact. But of course, we have already seen example of a solvable Lie group which does not admit a lattice. For example, the affine group of affine homeomorphisms of interval of real line, affine group of R. On the other hand, in the other world, so the semi-simple world, every connected semi-simple Lie group admits a lattice. In fact, both co-compact and non-co-compact. We saw that in the example of SL2R. I have to rush, unfortunately. But this is the most important fact actually I want to mention for my talk. This is the most relevant fact for my talk. This is Zassenhaus-Margolis lemma, so it's discovered by Zassenhaus in 1938 and rediscovered by Margolis in 1968. After 30 years, so let G be a connected Lie group. Then there is an open neighborhood of identity, sometimes called Zassenhaus neighborhood or Zassenhaus-Margolis neighborhood, such that any discrete subgroup of G of the ambient Lie group G generated by elements from this neighborhood is in fact nilpotent. So for example, in SLTR, that means you can't generate a lattice actually by matrices too close to identity, because the lattice of SLTR cannot be nilpotent. In fact, a lattice in some sense captures the content of the ambient Lie group, but this capturing is kind of indirect. For example, just to show an example, is a famous theorem of Margolis normal subgroup theorem. So we take a simple Lie group, SL2R as an example, but here we're going to take rank at least 2. So we start with SL3R. Its lattice is almost simple in the sense that any normal subgroup of a lattice is either finite or a finite index. In fact, the proof of this is quite remarkable, and I think I have read that Margolis calls this one of his most interesting proofs. So how do you prove that this quotient is finite? Well, he shows that using dynamics. He shows that it's amenable, and then it has Kazan's property T, so therefore must be finite. So it's a very interesting way of proving that a group is finite. I will skip this slide. I'm rushing actually. This is just to show that one of my recent works is on the theory of lattices of Lie groups. But prior to that, I was concentrated on studying discrete subgroups of diffeomorphism groups. So I will. So here's the diffeomorphism of the interval. Interestingly, so there's an isomorphism, in fact, to homeomorphism. Let's say from this diffeomorphism group to continuous functions. You see C0 is 0, 1. So the value at 0 is 0. So this space is maybe reminds you something. So there's a Wiener measure actually on the space, and because the diffeomorphism groups are infinite dimensional, so we don't have analog of Haar measure, and maybe you can use Wiener measure somehow. In fact, it has been used in at least one well-known paper, but we're not going that direction. So Wiener measure is not good for our purpose, it turns out. But what's interesting, so if we increase regularity of diffeomorphism groups, for example, instead of C1 regularity, we look at C1 plus epsilon, let's say C2 regularity, or even C1 plus epsilon regularity, epsilon bigger than 0, so an Hölder condition. Then the group starts, even though it is, of course, still infinite dimensional, but it becomes more tame. It starts behaving more like a Lie group. So I'm quoting 3 results. First, of Planter-Thurston, that any nilpotent subgroup of diff2 is a billion. On the other hand, the result of Franks shows that any finitely generated torsion for nilpotent group actually embeds in diff I. So in diff I, we have pretty much all nilpotent groups, if they are torsion-free, all finitely generated torsion for nilpotent groups. But in diff2, only a billion ones remain actually. And in between, they gradually vanish. So this is the result by Navas. So as epsilon goes from 0 to infinity, from 0 to 1. So we keep losing nilpotent groups. So diff2 becomes an interesting object for us. In fact, it's very tame in this sense, and also in some other senses too. So we try to treat it as a Lie group. So the question arises, what kind of Lie group? Solvable or semi-simple? And it turns out, it's neither one. So it has its own world and should be treated as such. the way I define it is discrete subgroups. I think the definition, yeah. So it's C1 discrete and C0 dense. So this mimics the situation when lattices, let's say semi-simple Lie groups, are Zariski dense, and of course they're discrete in the usual topology, the actual topology of the group, so Hausdorff topology. This is a bit bold statement. But is this enough? Well, I mean, I have obtained some results already with this definition, and I will maybe mention, I think I will mention at least one of them in the next slides. But the study of lattices, the theory of lattices, is really something of a future. I will talk about mainly just about my studies of discrete subgroups of diffeomorphism groups. And here's my, I think, first result, my first paper. So on discrete subgroups, I show that three groups admit a discrete representation in the diffeomorphism groups. And then the second result is from a preprint that so when I say discrete representation of diff I mean in C1 metric. So in diff I, we consider C1 metric, and in homeomorphism groups, we consider C0 metric. In C0 metric, there is no dense representation of any elementary amenable group. So elementary amenable groups cannot be lattices of diff I. On the other hand, interestingly, every finitely generated subgroup there admits a discrete representation, again in C0 metric. So there are interesting questions, of course, to ask. What about general amenable groups, for example, regarding the second theorem, or regarding the first theorem? What about if we increase regularity of the representation, make it, for example, C2 or C analytic? What can we say in those situations? I'm going to skip those questions now, but in my second paper, I prove this weak version of Zassenhaus-Margulis lemma, which I'm going to state in the next slide. But as a result of it, I was able to classify C0 discrete subgroups of diff I. So these are terms A, B, C from that paper. And okay, so for example, the third term says that basically any discrete C0 discrete subgroup of diff2 is in fact meta-abelian. These terms has been improved since then, and I will state the improved version in one of the next slides. And here's the statement of weak version of Margulis, Zassenhaus-Margulis lemma. The proofs are very analytic. I have to rush, unfortunately. I was not planning to show the proof, but I mean, even I won't. Basically, I won't have time to discuss even the statements. But I used these theorems in the previous slide to prove the characterization theorem of C0 discrete subgroups. So then people were actually telling me, encouraging me to find some applications of my study of discrete subgroups. And I want to quote this theorem from 1901 of Hölder. Now, Hölder is also the mathematician who introduced Hölder spaces, right? Hölder, we already talked about Hölder conditions, C1 plus epsilon class. But this fact and that Hölder space was never in Hölder's mind at the same time. That's kind of interesting. The proof of this is actually it's pure algebraic. So imagine a subgroup of homeomorphism group, orientation preserved homeomorphism groups, such that any non-identity homeomorphism from your group acts freely, has no fixed point. Then it's in fact a non-trivial fact claim that such a subgroup is necessarily abelian. Hölder's proof is in fact also purely abelian, so purely algebraic. So he introduces an essentially left order in the group, and then shows that it's Archimedean, and then pure algebraically shows that any Archimedean group must be abelian. The question here is that what if every unidentified element of gamma inside Homer R even has at most n fixed points for some uniform n, for example, when n equals 1. When n equals 1, this has been treated by Kovacevic and Solodov. First, it's an unpublished work, the Kovacevic in 1999 transactions and Farb-Franks 2003 transactions. And they show that gamma is isomorphic to an affine group. Remember, affine group of R, affine R, the two-dimensional solvable Lie group we were talking about. And when I was a graduate student, I started thinking about this question for general N. And then after I studied discrete subgroups, I saw a connection. My study of discrete subgroups was not for this purpose at all. Somehow, I recalled this problem, and then I was able to solve it using my studies. And this is a theorem from 2016. And here the theorems 1, 2, 3, you see these are improved versions of my theorems A, B, C. And in regularity C1 plus epsilon, I'm able to obtain this claim that any such subgroup, in fact, is isomorphic to a subgroup of affine R. And then more recently, in fact, I dropped that regularity condition. So in fact, in diffeomorphism groups, I'm able to say that, in fact, any such subgroup is a subgroup of affine group, and in fact, conjugate to a subgroup of affine group. In the homeomorphism group, you can say that, but it is the best example, the best claim you would hope is semi-conjugacy, and I obtained that. Now, these two theorems are different papers. The first theorem is an improvement of my results from the earlier version, basically by sharpening the tools that I'm using. The second theorem uses new tools and quite diverges from the first theorem. So now we have a classification of diffeomorphism groups and homeomorphism groups of I and R, that there's no difference, as I mentioned earlier. So well, I mean, there's a difference, but I mean, this is sorry, there's a difference between I and R in the diffeomorphism group. In the homeomorphism case, there's no difference. But and in the diffeomorphism case, I obtain a complete characterization, basically, and so I do so also in the homeomorphism case.
You have almost 2 minutes.
I will stop here.
Thank you. Thank you for the nice presentation. Now let me stop the recording.